Hello everyone, this is John, and today we're going to look at projectile motion and the movie Martian. So recall a scene where a Mars ascent vehicle is launching off the surface of the Mars. So this is basically what happens when a spacecraft launches off the Martian surface. So a similar thing happens on the surface of Earth, but the only thing that is different is the gravitational acceleration constant. So assume there's a launch site right there. If it launches off the surface, it basically becomes a projectile motion after MECO. MECO being the main engine cutoff. After the main engine gets cut off, the vehicle enters a free fall state. Therefore, it becomes a projectile motion. But right at the max point, the highest point of this projectile motion, where it is an apogee, it has to give additional acceleration, a horizontal one this time. So I depicted here as delta V. It has to give that little boost in order to enter a safe low Martian orbit. This can be proven by the concepts we covered prior to this lecture. So now we're going to look at something that might be a little new for you guys. So here, it's a little hard to get the angle right, but we're going to do the projectile motion. But in order to really calculate just about anything, we have to know the gravitational constant of the Martian surface, which is G. Since we are not on the surface of the Earth, G is not going to be 9.8 meter per second squared. So we have to manually calculate it. But instead of just searching for the value on Google, we're actually going to calculate it by hand. So here are the constants that we need in order to derive the G value of the Martian surface. So we got the radius of Mars and mass of Mars. We also have to use something called Newton's first law, which we learned in the first unit of grade 11 physics. It's F equals to ma. This is a very important concept we have to remember in order to solve this question. Also recall a universal law of gravitation. In this case, it's a little different from the formula we used prior to this, as this one doesn't contain a negative sign in the numerator. So universal law of gravitation. So this formula applies to any kind of cases where there are two objects. So F equals to G m1 m2. We're just going to remove the bracket. And then we're going to say, r to the square of 2. Sorry, not squared. I mean r squared, not r to the power of 2. Pretty much the same thing, but just, sounds better. So F equals to r, F equals to G m1 m2, and r squared out. Move the camera a little closer to the equation so you guys can see it better. So as you guys can see, this is the universal law of gravitation. Then how do we calculate the exact value of the acceleration, like gravitational constant of the Martian surface? Well, here we go. There we go. So we're gonna get a different colored pen, and we're gonna proceed. So say there's a person standing on the surface of Mars. There's obviously a force acting, which is Fg. What is Fg? Fg, according to the universal law of gravitation, since Fg is a force between that person and Mars as a celestial object, universal law of gravitation can act here, since it's a gravitation, it's an attraction between the planet and the person, right? So Fg in this case is going to be Gm m2 over r to the power of 2. But there's also one more thing that we learned as I told you. It's F equals to ma, right? So in this case we can say that. So in this case we can say that here. Let's say the mass of this person is mp, and the mass of the planet Mars is me. Sorry, mm. So mp times a equals to Fg equals to G m1 m2 r to the power of 2. So here we can simply get the value we want to get by canceling out here. Since there's m1 and m2, we're going to say m1 is the mass of the Mars, and m2 is the mass of the person. So we're going to label this, for convenience sake, mass of person, and m is mass of Mars, right? Which is a constant. So here we can clearly see that this side equals to this side, so we can just get rid of Fg here, right? And we can cancel out MP, since these are basically the same value. So now we're gonna calculate the value of A being the gravitational acceleration constant of Mars, G, right? So here we're gonna derive the value by just saying, because it's a surface gravity, FMA, you know, it applies. So what is MM, the mass of Mars? It's, according to Google, it's 6.39 plus 10 to the power of 23. We just have to, and what's the value of G? As you recall, the universal constant of gravitational, of gravitation is about 6.67 times 10 to the power of negative 11. Don't forget the negative sign. And we're going to say this is going to be divided by r to the power of 2. And r of the radius of Mars, in this case, is 3.389 kilometers. So we're going to say squared kilometers. And add a bracket right there. Right, so we do have to convert it to meters, which is 3,389,000 squared. So if we just perform the calculation, we get a value like 338. So as you can see, 338,9,000 squared, which equals to 3.710936,769. There you go. We got the value of the gravitational acceleration on the surface of Mars. So Google tells me the value should be 3.754, which is pretty close to the value we got. So this proves that the equation works. In this case, we're not going to use the value that Google derived for us, because then our hard work is going to be nothing. So we're going to use this constant that we derived using the first law of Newton's blah blah blah, and the universal law of gravitation that we learned. You know, so we derived this constant value, 3.71. We're just gonna write it up to 3 significant digits. So okay, there you go. So we got the constant value, and we just have to work on our projectile motion. Thank you, and have a great day. Bye.